In this video, we will begin to talk about experimental research. The book starts off with a great example of an experiment. A couple of researchers proposed the idea that the more witnesses there are at an accident or some type of crime, the less likely any of them would be to help out the victim. Subjects in this case feel less responsible for helping, and this is known as diffusion of responsibility. Their idea was consistent with some reported real-world examples. There's a famous case of Kitty Genovese, who was assaulted and later murdered. There were several witnesses to this murder, and they all failed to help. But one story isn't really convincing evidence. From the Kitty Genovese case, there was really no way to know if, for instance, there were fewer of them or witnesses, if they would have helped out or not. So these researchers actually went out and tested their hypothesis. They created a simulated emergency in a laboratory setting. Subjects were isolated in a room and were instructed that they would have a discussion about university life with other students over an intercom system. Then a Confederate would have a planned fake seizure in which they cried out for help over the intercom. Participants were told that the discussion over the intercom happened with either only one other student, the victim, or that they were also virtually talking to two other students, and in some cases it was 5 other students. So the only difference here was the number of subjects also present with the Confederate, either no one else, 2 other people, or 5 other people. Since this was the only manipulation, any difference in the tendency for the subject to reach out for help would have been caused by that manipulation. The results from this experiment showed that the likelihood that the participant left the room to go get help decreased from 85% to 62%, all the way down to 31% as the number of witnesses increased. In this way, they were able to establish a causal relationship between the likelihood of helping and the number of witnesses that were present. These researchers used an experiment to test this, and this is one of the most powerful tools in our researcher toolbox. So we can define an experiment as a type of study designed to answer specifically the question of whether there is a causal relationship between 2 variables. Another way of saying this is whether changes in an independent variable causes a change in a dependent variable. This is the goal of the experimental research strategy. It's to establish this cause and effect relationship between multiple variables. You're already probably familiar with the different types of variables, but just to put a technical definition on it, an independent variable is the variable that the experimenter manipulates. This is the presumed cause. And the dependent variable is the variable the experimenter measures. This is the presumed effect. The interpretation from these two are that the effects are always on the dependent variable, resulting from manipulating an independent variable. But that doesn't mean there always has to be an effect. It's entirely possible that there could be no effect at all. But if there is an effect, we know the directionality of it. It's never the effects of the dependent on the independent, it's always the effects of the independent on the dependent variable. Here we're just going to go over a few examples. Let's say a researcher wants to study the effects of note-taking on test performance. In a class, some students are only allowed to take traditional pen and paper notes. Then other students are only allowed to take notes on their laptop. Then all of the students take a test over the material, and the researcher then measures the difference in test performance between the paper and electronic note groups. Think about this and try to identify what the independent variable is, how many levels or conditions are in the IV, and what the dependent variable is. So the IV here is the type of note-taking. This is what the researcher is manipulating, either electronic or paper and pen. And there are 2 levels or conditions in this IV, which is the paper condition for 1 and the electronic condition for 2. The different levels in an IV are also referred to as experimental conditions. Then the dependent variable is test score performance. That's what we're measuring. Okay, so here's one more example. Here, say a researcher wants to measure the efficiency of sleep in adolescent children. They think that when you play a calming auditory sleep aid, this would help sleep. They had kids either sleep with a special radio playing or sleep in silence. What they found, hypothetically, with this is that kids who had the sleep aid woke up fewer times throughout the night compared to kids who did not get the auditory sleep aid. So think about here, what is the IV, the DV in this example? So here the IV, or independent variable, is the presence of auditory sleep aids. There are again two levels or conditions to this IV, having the sleep aid or not having the sleep aid. And the dependent variable is the number of times the kids wake up during the night as an index of sleep quality. With these two examples, the independent variable has two conditions, but there could be more than that. There could be 3 or 4 or 5 conditions. With the sleep example, they could have 3 conditions by not only having the sleep or no sleep aid, but they could have 3 different kinds of sleep aids to see which one works best. Before we move on, we should take a second and talk about the difference between true and quasi experiments. Any kind of true manipulation means that there has to be an active intervention on the part of the experimenter. You create the groups and you place people in those conditions. When you compare people on a dimension that they naturally differ on, this is a quasi-experimental variable, not a true experimental variable. We'll take handedness as an example to prove our point here. It's completely valid to study the effects of right-handers versus left-handers on some type of performance. However, we can't truly manipulate handedness. If you come into the lab, I can't tell you to be left-handed for the day. You either already are right-handed or left-handed. So I can't truly assign people to different groups. We can still compare these groups, but we have to note that they are quasi-variables. With experiments, it's important to try and control for as many things as you can. Here we have an example. We have a light condition as our independent variable, workers working in a factory either with light or no light. Say in the light condition, that leads to better worker productivity. But also we notice that the light from this experiment causes a buzzing noise, a noise that wasn't there in the no light condition. Here we can't really be sure if that bump in worker productivity is due to our experimental manipulation, light, or this other factor of noise that was only present in one of the two conditions. This gets at the idea of confounding variables. This is an extraneous variable that systematically varies along with other variables under investigation, and therefore provides an alternative explanation for our results. When we design experiments, we need to make sure that we control for all possible confounds. You control for or minimize any kind of variability in variables other than those that you study. This means that you test people in the same room, have everyone perform the same test, and make sure that subjects are randomly placed into different groups to make them as similar as possible. There could be tons of extraneous variables that differ across samples. This could be general abilities, gender, amount of exercise, and so on. IQ is a good example of an extraneous variable. IQ can definitely affect a wide array of tests or tasks. But as long as there are some individuals with both high and low IQ in all of your experimental conditions, this shouldn't really be a problem. It's when there's just one experimental condition with people with higher or lower IQ than the other groups that this would turn into a confounding variable. The need to eliminate different explanations of a phenomenon and the need to control for these factors is well illustrated by the true story of Clever Hans. More than 80 years ago, a German school teacher presented to the public a mathematical horse named Clever Hans. This horse knew how to solve various math problems. When his trainer gave him addition or subtraction or multiplication problems, Clever Hans would answer them by stomping the correct number out with his hoof. If the answer was 4, he would stomp 4 times. And the horse was actually really accurate with these math problems and would rarely get one wrong. This had baffled everyone who saw this. Even one Berlin newspaper reporter wrote that this horse is going to give men of science a great deal to think about for a long time to come. No one knew how this horse was doing this, and people questioned on whether this horse could actually solve these math problems. Well, a psychologist then took up the case and systematically studied the horse's ability. This psychologist manipulated different conditions of the horse doing math problems, creating different situations that would allow him to test alternative explanations. It turns out that Clever Hans was a really careful observer of human behavior. As it was tapping out its answer, it would closely watch the head of the trainer or other people in the audience. As Clever Hans approached the answer by stomping over and over again, the trainer would start to tilt his head just slightly, and then Hans would stop stomping. Likewise, people in the audience would slowly lean in as Hans got close to the answer, and then would notice these postural changes and then stop stomping. This horse wasn't actually able to solve the math problems, but it was really sensitive to visual cues. When the horse would try to solve problems in a way that the trainer didn't know the answer to the problem, then the trainer wouldn't involuntarily change his body posture, and the horse therefore wouldn't be able to solve the problem. Or if the horse's view was restricted and therefore couldn't see the trainer during the problem, this amazing ability again just disappeared. So this amazing ability to solve math problems was really just the horse that was sensitive to the changes in the observers. Now we can use this case in methodology courses, and it shows us the need to look for and try and control for alternative explanations. Okay, to start to review, the four basic elements of experiments are 1. Manipulation. We take a variable and we change it to have at least two different conditions. Then we take a second variable and then we measure that. We then compare our measurements in one condition compared to another, and then we try and control for as much as we can that we aren't specifically manipulating. And also, we should design experiments with parsimony in mind. Yes, we need to try and rule out alternative explanations, but that doesn't mean that we have to make these extremely complicated experiments or designs. You should design your experiments and theories as simply as possible while still being able to explain as much of the phenomenon as possible. Okay, last slide for this video. We need to briefly touch on the idea of statistical significance. Whenever you compare two sets of scores, the two sets will never really be exactly the same. If you were to recruit different subjects and do the same thing the next day, the scores will most likely be different. As long as these differences are pretty small and random, they're usually meaningless and just due to chance. Say you draw a line through the center of a movie theater and compute the average level of self-esteem for the right side and the left side. Say it happens that the left side of the theater has higher levels of self-esteem than the right side. These two averages are different, but this result is most likely due to chance, and we wouldn't interpret that as evidence for some kind of weird phenomenon where high self-esteem individuals tend to sit on one side of the movie theater. In experiments, we do compare different conditions, but just because there's a difference doesn't mean that we can automatically conclude that our manipulation caused that difference, because it could be due to chance. Before we interpret anything, especially when making a cause and effect claim, we have to conduct a hypothesis test and show that the difference is statistically significant. A significant finding means that the difference is large enough for a hypothesis test to statistically rule out chance as a possible explanation, and therefore you can say that the difference must have been caused by the treatments or the conditions. We'll get into the details of this later on in the course, but for now, just keep in mind that any differences that we evaluate must be statistically tested before we can make any conclusion. Okay, so that's it for this video. See you next time.